The disk method, a volume of revolution. Our objectives in this lesson are to develop the use of the disk method for calculating volumes of revolution. Also, we want to use Riemann rectangles and the disk method for constructing integrals. To develop the disk method, it is derived from a formula for volume of a cylinder. So notice in this image that if you revolve a rectangle about one of its edges, you get a cylinder. You can still see the rectangle inside of the cylinder, and if you were to twirl it around the x-axis like that red arrow is indicating, you would get the cylinder shown here. Notice how the height of the rectangle is now replaced with the word radius, and how the width delta x of the rectangle is now the height of the cylinder. So we ask, can you make this connection between the rectangle with height of f of x and width delta x to the volume of a cylinder, which is volume equals pi r squared h. And in this case, we see that the radius is given to us by f of x. That's not always the case. Sometimes we have to modify things, but often you'll find that f of x will be the radius function. And the height of the rectangle, or the width of the rectangle, delta x, is the height of the cylinder. So we can take the volume formula, which is v equals pi r squared h, and we see that in terms of integrals, we're going to use v equals pi times f of x squared delta x, and we're going to integrate with this formula. So just to demonstrate this, I drew a simple curve f of x. The interval is from a to b. And we're used to seeing this with area beneath the curve. We would say, well, let's shade everything from a to b under the curve and above the x-axis. And now I've shaded it green. And when we first wanted to approximate this area, before we learned that we can use integrals to do this, we would draw in Riemann rectangles. And these Riemann rectangles would give us an approximation of the area under the curve. Well, eventually we would make the rectangles skinnier and then have limits to infinity, and we would get this to fit the curve perfectly, and it would be an exact representation of the area. Now, remember when we started this lesson, we said, what if we revolve that rectangle about its edge? So here, the first rectangle is revolved around the x-axis, then the second, then the third, and so on. And if we keep revolving these rectangles, we get these disks that approximate the volume. And then we say, well, what if we made each of these disks skinnier like we did with the rectangles? And we have a limit that as the number of disks goes to infinity, it will give us a smooth and perfect representation of the 3D figure. And it would look something like this. So that's what we're doing with the integrals. The integrals are finding this volume. As the number of rectangles or disks go to infinity, we get a smooth representation of the three-dimensional figure. So our volume formula has now become v equals pi times the integral from a to b of r of x squared dx, where r of x is the radius function, which is often the function that you're using for your curve, but sometimes needs modification. So in the volume formula, we have v equals pi r squared h. We see that the definite integral accounts for changing radii by substituting the function f of x in for the radius. Since the radius is squared in the volume of a cylinder, so is f of x squared. Only we call it r of x to relate it to the radius. Finally, the sum of all of the cylinder volumes is accounted for by the integral itself. Recall that the integral is shaped like an elongated S because it takes over the task of summing infinite rectangles, or in this case, cylinders, from the sigma operator. And you see the sigma operator there with the disks, and then the limit to infinity, and then it becomes the definite integral. So here's our first example. The shaded region is bound by the function f of x equals x plus 1 squared and the x-axis. We have the lines x equals 0 and x equals 2. Those are the left and right bounds of the shaded region. Find the volume of the solid formed by revolving the shaded region about the x-axis. notice my little red arrow going around the x-axis, and if we take this shaded region and we revolve it around, we get this three-dimensional figure. It's not quite a truncated cone because the edges are curved, not straight, but a truncated cone would be an estimate or an overestimate of this volume, and we would expect it to be something less. So we want to set up the integral. And to do that, we recall our formula. V equals pi times the definite integral from a to b. We see that since we're going around the x-axis, the a and b values come from the x-axis, so from 0 to 2. Our function has to be squared, but since our function is x plus 1 squared, and that has to be squared, we get x plus 1 squared squared. And dx, because we're going around the x-axis, and our Riemann rectangles would have to be drawn perpendicular to the x-axis. Let's simplify the integral. X plus 1 squared squared is x plus 1 to the 4th. And we can integrate this by expanding the polynomial. I can take x plus 1 to the 4th and use a binomial expansion theorem, or I can use Pascal's triangle, but it's easier and quicker to evaluate using substitution with integration. So let's set u equal to x plus 1. Then the derivative of u is equal to the derivative of x plus 1, which is 1 dx. And we also want to change the bounds of integration. Since the original integral goes from 0 to 2, those are x values, we want to change them to u values. So take 0 and plug it into u equals x plus 1. Well, then u equals 0 plus 1. The new lower bound would become 1. And then we take 2 and we plug that into u equals x plus 1. We get u equals 2 plus 1. The new upper bound would become 3. And now we can rewrite this integral in terms of u. We have that volume is equal to pi times the definite integral from 1 to 3. We've replaced x plus 1 with u, so it's now u to the 4th du. And this is a simple power rule for integration, and we can find the antiderivative. So the antiderivative is pi times 1/5 u to the 5th, and now we need to evaluate it using the fundamental theorem of calculus. And if we plug in the top bound of 3, we get 3 to the 5th over 5 minus the bottom bound of 1 is 1 to the 5th over 5. And we can simplify this. The volume is 242 pi over 5, which is approximately 152.05 cubic units. Okay, so here we have example 2. It says the shaded region is bound by the function f of x equals the square root of sine x and the x-axis on the interval from 0 to pi. Find the volume of the solid form by revolving the shaded region about the x-axis. So notice that this revolution here is about the x-axis. And whenever that's the case, you always have to draw your Riemann rectangle so that it is perpendicular to the axis you're revolving about. And then that tells you that the width of your rectangle is delta x. So that means you will need an integral with dx. So we use the Riemann rectangles as a reference to know what variable we should be focusing on. So we can go straight to our volume formula. Volume equals pi times the integral. We see our shaded region starts at 0 and ends at pi. And our function f of x is the square root of sine x. We have to square our function and then dx. So remember, this is derived from volume of a cylinder, which is pi r squared h. The pi is a constant. We have that. The r squared, the radius. Well, we see that the radius changes throughout this region, and the distance from the axis to the edge of the region is given to us by the function square root of sine x. So that means our radius is square root of sine x, so that's why we're squaring it. And the height is this entire length, which the integral is going from 0 to pi dx, and that takes care of the height. So again, we just like to see the connection between the volume of a cylinder and the volume by disk method formula. So now we can simplify. We see that the square root of sine x squared simplifies to simply sine x. And the antiderivative of sine x is negative cosine. And then you use your fundamental theorem of calculus. And cosine of pi is -1, but the negative of -1 is 1, minus, and cosine of 0 is 1, but there's a negative in front of the cosine, so it's -1, and 1 minus a -1 is 2. Don't forget the pi out front, so it's 2 pi, and that is the volume of the solid of this region revolved around the x-axis. So example 3, the shaded region is bound by the function f of x equals x squared plus 1 and the y-axis on the interval from 1 to 2. Notice the interval is y from 1 to 2. And in the bottom it says find the volume of the solid formed by revolving the shaded region about the y-axis. And when we do this, it's going to need to have a Riemann rectangle drawn perpendicular to the axis you're revolving about. And when we do this, we see that our rectangles are horizontal, and this means that we need to set up this integral as a function of y. We see that we have a shaded region that is bound by the function f of x equals x squared plus 1 and the y-axis. So here's the y-axis. This is our shaded region. And it's on the interval. Notice they're using the y variable from 1 to 2. It says find the volume of the solid formed by revolving around the y-axis. So that means we should draw our little arrow saying we're revolving this way. And as I just said in the previous example, we should always draw our Riemann rectangles perpendicular to the axis we're revolving about. Well, when we do that, we see that the width of this rectangle is delta y. And if we're dealing with delta y, that means our volume should be the integral with a dy, which means that our bounds for the integral should come from the y-axis. We see it goes from 1 to 2. So we can write our formula as volume equals pi from 1 to 2. We need a function of y squared dy. Well, this is a function of x. So f of x equals x squared plus 1. I can write that as y equals x squared plus 1. We want to turn this into a function of y, so it's y minus 1 equals x squared. And when we take the square root of both sides, we get x is equal to plus or minus the square root of y minus 1. The positive square root would be the right-hand side of the parabola. The negative square root would be the left-hand side. We don't have the left-hand side, so we only want the positive square root. X equals positive square root of y minus 1. And that's our function of y that we want to plug into our formula. So volume is equal to pi times the integral from 1 to 2. Remember, 1 to 2 came from the y-axis. The square root of y minus 1 squared dy. So now when we integrate, we have y squared over 2 minus y from 1 to 2. Volume 2 squared over 2 is 2 minus 2, that's the f of b, minus the f of a is 1/2 minus 1. We get a volume of pi over 2. So in these two examples, we see that the disk method starts with setting up the integral correctly. And in this second example, or in example 3, I should say, the focus was on the y-axis. We were revolving around y. Draw your Riemann rectangle perpendicular to your axis. You needed a function of y. That is the part you had to demonstrate that you understand with this example.